Hello, welcome back. Okay, so we're continuing to work through chapter 2 of the book. We've reached the last main section, the section from the last section from the what I call the main content of chapter 2. And so far, the ideas that we've been working with have been fairly grounded, right? We've talked about the integers. What does it mean for an integer to be even or odd? What does it mean for one integer to divide another one? What's the greatest common divisor? What does that mean between two integers? Now, we made these concepts hard. We made them hard by insisting on precise definitions and using them in proofs, things like that. But what we've reached now is something different, something that is on its face abstract and hard to comprehend. And it's this idea of modular arithmetic, taking things, one integer mod another integer. So here's definition 2.14. For integers a, r, and m, we say that a is congruent to r modulo m, and we use this notation, a, an equal sign but with 3 lines, r, parentheses, mod m, if this thing happens. So this is what we say, a is congruent to r modulo m if m divides a minus r. Okay. This is not evens are n equals 2k. This is not the greatest common divisor is defined to be the greatest thing that divides. That's a common divisor. This is complicated. First of all, the thing that we're underlying, the thing that's being defined, uses words like congruent and modulo, probably words that you haven't used this week so far. And the notation's a little funky, a new symbol was introduced. And even once you get down to the heart of it and say, well, okay, so we say this, but when do we say that? Well, what is the actual definition? We say m divides a minus r. Not obvious that this should be anything that we should actually care about. It turns out that it's very important, but it's not on its face. It doesn't seem very important. So there's, right off the bat, this is complicated, right? So I want to do some examples first thing to sort of at least start to understand what this is even saying. But first, let me just spend 1 minute just saying a few words about this. There are times in your math courses where a high-level concept appears because it's needed at that moment to sort of advance the theory or to prove something or whatever, and then it falls off. And perhaps never again in that course, and certainly not in later courses will you see that high-level concept. There are other high-level concepts which poke their head out and they keep appearing throughout that course, throughout future courses. They are just so important in math. Mods are in the latter camp. This is a tough idea, and it was not an easy decision to introduce it in only chapter 2 of this book. It's one of the hardest ideas that you will, concepts that you will encounter, that you encounter in this course. Okay, it's one of the hardest concepts, but it's very important. Okay, it's extremely important, and it's good to do it early because one, it fits in right now. I mean, we're talking about divides and stuff, so it fits perfectly right now. And if you introduce it early, we can spend the rest of the course, a few other times, reintroducing that concept to become even more familiar with it. And it's not just in this course that it's going to be important. In so many of your future courses, mods will appear. Certainly, if you take an abstract algebra class or a number theory class, in those classes, it's going to be a very important idea. And it might also appear in maybe a combinatorics class or a theoretical computer science class. But even beyond this precise definition involving integers and divides, there's a much more general concept at play, which that is even more important and will appear in many future courses. So at the end of this video, I will come back and sort of tell you a little bit about that, so you can look forward to how many instances this general concept is going to reappear in your future courses. So that's to come. But anyways, just at the start, just keep in mind, this is really important. This is it's complicated, it's confusing at the start, but in the end, in 2 years, if you're a math major and you're just taking intro to proofs, in 2 years, you're gonna master these things because you're gonna have used them so many times. Anyways, let's start doing some examples. Okay, so what does this mean? So 18 is going to be congruent, so it's an equal sign with 3 lines. 18 is congruent to something mod 7. So let's figure out what that something will be. Okay, so maybe I'll give you this first one. 18 is congruent to 4 mod 7. So why is that the case? Why is 18 congruent to 4 mod 7? Well, first of all, because it satisfies the definition. But I'm going to give you 2 justifications. The second one is actually going to be that it satisfies the definition. The first one is is sort of the first way that I want you to think about it. Even though it's not the definition, it's sort of the best way to start. So if you took an 18 and you divide by 7, the thing it's congruent to is the remainder. Okay. So 18, so one reason why this is true is because 18 equals 7 times 2 plus 4. Okay, so if you use the division algorithm, what we're saying is that 18 and 18's remainder, when you're dividing by that number, are congruent. So for reasons that will become more clear throughout the next couple of videos, and certainly more clear over the next 2 years of your education, relating a number to its remainder when you're working mod, when you're dividing by this thing, is a very, very important thing. It's extremely useful. You would be shocked how useful it is. Cryptography, a lot of cryptography, the high-level cryptography stuff relies on this exact thing, okay? So if you take a cryptography class, you will most certainly be studying mods. Okay, so similarly, if you take 13 and divide by 4 now, what's the remainder? 1, right? It goes into 12 evenly, so it goes into 1. So with 13, there's 1 left over. So one way to write that is 13 now is equal to 4 times 3 plus the remainder of 1. Okay? So 13 and 1 are congruent. Congruent meaning they're almost equal. That's one way to think about it. The equal sign, it almost looks like an equal sign. And that's what I want you to think about. 13 and 1 are almost equal when you're considering this mod 4 context. So in a mod 5 context, what would 35 be congruent to? Again, think about remainders first. So what is the remainder when you take 35 divided by 5? 0, right? There is no remainder. So first of all, think about it like 0. So 35 is first 5 times 7 with no remainder. Okay? Step off. Okay, so finally 3, if you take 3 and you divide by 13, what's the remainder? Well, it's 0 with the remainder of 3. Okay, so here we have 3 congruent to 3. Okay, and one way to regard that, again, if you start these numbers on the left column, then you include the mod, and you say what are the unique, if I was going to turn this into the division algorithm, what are the unique numbers I can put here and here? You'd put 0 here and 3 there. Okay. Remember, this number has to be between 0 and 12. So only 3 could work with the quotient being 0. Okay, so that's the first level. Understanding that one way to think about this is as the remainder. Now, that's only half true, but it's the good first step. But another reason why 18 is congruent to 4 is simply it satisfies the definition. So is it true that 7, the mod m, divides a minus r. So a is on the left, r is on the right. So this is 18 minus 4. Does 17 divide 18 minus 4? Well, what's 18 minus 4? 14. Does 7 divide 14? Yeah, 7 does divide 14. So yeah, check. I don't know. I guess I'll put a check there. It's true, right? 7 does divide 18 minus 4. So that confirms that this is a true statement, that 18 is congruent to 4 mod 7. Okay? If you haven't been pausing the video to think about these things, feel free to pause at any point. What are the next ones? So if we want to check the definitions, we put the mods first, like 4, 5, and 13. Then we put a divide symbol, and we see, is it true that 4 divides 13 minus 1? Is that true? Does 4 divide 12? Yeah, 4 does divide 12. What about, does 5 divide 35 minus 0? The answer is yes, it does. 5 does divide 35. And does 13 divide 0? 3 minus 3. Yes, it does. Okay, so that is the first way to think about this, is that AE is congruent to R, mod M, if when you take A divided by M, the remainder is R. Okay. But that's only half the story, because although things are congruent to the remainder always when dividing by the mod, the definition is actually actually more general. So let me write over here. But it doesn't have to be the remainder. It doesn't have to be the remainder. For example, 16 is congruent to 9 mod 7. And y, so here's my because column. Y is 16 congruent to 9. Well, it does satisfy the definition. Is it true that 7 divides 16 minus 9? What is 16 minus 9? 7. Does 7 divide 7? Yes. You looked at back to the definition 2.8, definition of divides. A divides B if B equals A times K. Yeah, it all works out. K would be 1. So, okay, so now it's time to expand your understanding a little bit. Things are congruent to the remainder when dividing by the mod. Also, two things are congruent if they have the same remainder when divided by the mod. If you take 16 divided by 7, you get a remainder of 2. If you take 9 divided by 7, you get a remainder of 2. You get the same remainder in both cases. That means that they are indeed going to be congruent. Okay? 16 would not be congruent to 8 mod 7. I would have to put a line through it. It is not congruent to 8 because they have different remainders when divided by 7, 2 and 1. Make sense? Okay. So it really is all coming back to remainders, but you just have to kind of expand your brain a little bit here. Okay, so 1 is congruent to 13 mod 7. Why? Well, if you take, not 7, that's not correct, 4 mod 4, that's what I meant. So if you take 1 divided by 4, what's the remainder? It's 1, right? 1 apple divided among 4 people, no one gets any, and there's 1 left over. Okay, so the remainder is 1 here. 13 apples divided among 4 people, everyone gets 3 with a remainder of 1. So in both cases, dividing by 4 gives you a remainder of 1, so they're congruent. So does 4 divide 1 minus 13? 1 minus 13 is negative 12. Does 4 divide negative 12? Yeah. Negative 12 over 4 is negative 3. That's an integer. Okay. Give you a couple more. Maybe this is a good pause the video moment. What is 32 congruent to mod 5? Now, there are actually infinitely many answers. Can you think of some? What other number? So 32 divided by 5 leaves a remainder of 2. So what are other numbers which, if you divided them by 5, would leave a remainder of 2? 2, 7, 12, right? 12 divided by 5, remainder of 2. 17, 17 divided by 5, remainder of 2. 22, 27, 32, 37, 42, 47, 52. I happen to choose 52 here. But any of those numbers you could put right there and it'd be a true statement. 32 is congruent to all of them. Okay? So, and it's true because we can also check the definition. Does 5 divide negative 20? Yes, 5 does divide negative 20. 32 minus 52 is negative 20. And one last one, squeezing here. Negative 3 is congruent to 7 mod 5. So here's another mod 5 one. Now the negatives are always a little hard to think about. If you write out negative 3 with the division algorithm, the remainder is 2. Okay, a little tricky to think about. But the 7 divided by 5 also has a remainder of 2. Again, you could check the definition. Does m divide negative 3 minus 7? Well, what's negative 3 minus 7? Negative 10. Does 5 divide negative 10? Yes, it does. Okay, good. So, it's a tricky idea. The big idea is we have certain integers which, in certain contexts, it's very useful to think about them as being equivalent to a bunch of other integers or congruent to a bunch of other integers. So in the mod 5 sense, we want to think about 32 and 52 as being kind of like the same. Kind of the same. We want to think about negative 3 and 7 as being kind of the same when you're thinking in mods, in terms of mods. Okay, so that's an important idea. Now, I haven't told you why. I've just told you, believe me, you will see this idea in many more of your future courses, and not only because it's so useful, but for now, that's an important concept. It relates back to this idea of divides and remainders, so it's the natural place to put it. Now, to understand this on another level, let us go ahead and look at some metaphors. Okay, so let me pause the video and I'll get this set up. Okay, let me give you a couple metaphors, ways to think about mods. So the first way is actually, it's how I thought about it when I first learned about mods. So I sort of invented this metaphor in my own head as a way to sort of grasp this definition. Okay, so this was many years ago. Let me share it with you. It worked well enough for me, so let me see how well it works for you. Okay, so imagine you have a box. Okay, so now let's be working mod 6. So you have a box, and let's suppose you have 14 balls in the box. Okay, now so since we're working mod 6, I'm going to put layers of 6 at a time. So 6, 6, and then 2 left over. It's convenient to do it like that because then 2 is your remainder when you're dividing by 6. Okay, you have 14 balls in this box, and here's the rule. Because we're working mod 6, we're allowed to remove 6 balls at a time. Okay, so with 14, if you remove 6, that drops you down to 8 balls. And let's suppose you remove 6 more, that drops you down to 2. Okay, so because 14 balls turned into 2, using this procedure, removing 6 at a time because we're working mod 6, because 14 reduced down to 2, that means that 14 is congruent to 2 mod 6. The idea being, things are congruent if you're if you're working mod 6, you can always add 6 or subtract 6 at a time to find something else that you're congruent to. Okay, so 8, for example, also we saw along the way, right? 14 went down to 8. So because 14 went down to 8, using this moving 6 at a time, 14 and 8 are also congruent modulo 6. Alternatively, you could think about, well, they have the same remainder. So if you started with 8 and you removed 6, you get down to 2. That's the same remainder as when you started with 14. So that's another way to think about 14 and 8 being congruent. So again, the idea with the boxes is to sort of say, if you're working mod 6, you can always add or subtract 6 at a time, and nothing changes. And those are considered congruent. In a sense, in this mod sense, nothing changes. You still get something else that's congruent to what you started with. Okay, so that's 6. What about, let me just give you another example. So let's work mod 4 now. So what are some things which are all congruent to each other mod 4? Well, using this this balls and boxes analogy, let me give you 3. So if you have 5 balls in a box, or 9, or 13, okay, in all 3 of these cases, if you remove 4 at a time, because we're working mod 4, if you remove 4 at a time, in all 3 cases, you get down to a single ball in the box. So what were the starting numbers? 5, 9, and 13. So 5, 9, 13, and 1, by the way, are all congruent to each other, mod 4. Because, again, by removing 4 at a time, or you could even do it in reverse and add 4 at a time, from any one of those numbers, you can get to any one of those other numbers. One way to think about it. The other way is reducing them all brings you down to 1 in each of the cases. Okay. So because they have the same remainder left over, removing 4 at a time, they must all be congruent to each other. Or, going from 5 to 9, you just add 4, 9 to 13, you add 4, 13 down to 5, subtract 4 twice. In all those cases, you can move between the numbers just by adding the mod or subtracting the mod as many times as you need. Therefore, these numbers are all congruent to each other. Okay, so that was my my undergrad mental analogy. I probably didn't actually involve balls and boxes. That's just a way to make it more, visual and concrete. It was more of just adding and subtracting the mod each time. But that was the basic idea. You have 14 of something or 13 of something or whatever. You get to subtract or add the mod as many times as you want. By the way, that also applies for negatives. So, if you had 1 ball and you're working mod 4, you could subtract 4 to get down to -3 balls. Okay, now you can't actually have -3 balls. I guess you go into debt by 3 balls or something. But anyways, it also works for that. So you carry it into negatives, perfectly fine. You can continue subtracting 4. So 13, 9, 5, 1, -3, -7, -11, all those numbers are congruent to mod 4. Congruent to each other. Okay, does that make sense? Okay, now let me pause and set up my next analogy, which is clocks. This next metaphor is about clocks. So this is a clock showing 10 o'clock. And if you're in Gen Z, you maybe I should introduce this. This is what clocks used to look like long ago. Today they look digital, but these are the clocks that a lot of people grew up on. So this clock shows 10 o'clock. And if someone asked you, what time is it going to be in 4 hours, what would you say? Would you take 10 plus 4 and get to 14? 14 o'clock? Or some places outside the USA, some military people within the USA might accept 14 o'clock. But that we wouldn't say it's 14 o'clock. We would say it is 2 o'clock. Okay, so in 4 hours, it's going to be 2 o'clock. So 14 and 2 are congruent. They're the same. Mod 12, they're the same. So if a military person says 14 and you say 2, well, that's okay, because mod 12, those 2 numbers are congruent. Next, I have a clock This one shows 2 o'clock. And the question is, what time is it going to be in 27 hours? Well, you could take 2 plus 27, that gives you 29. Well, as far as I'm aware, no one says 29 o'clock. So what is 29 congruent to mod 12? What would be the time on the clock that would be congruent to? Well, in 27 hours from 2 o'clock, well, you go around the clock twice, right? A full day later, it's the same time on the clock, still 2 o'clock. So from 24, you just have to go up by 3 more. That gets you to 5 o'clock. Okay, so 29 is congruent to 5 o'clock. Make sense? So you've been thinking in terms of mods before. Any time you move from 10 to 10 o'clock, oh, in 4 hours it's going to be 2. You were using mods, that you were working in mod 12. Okay. Now, does it only work for mod 12 though? No, it actually doesn't. As long as you switch out your clock, it'll work. So this is so for mod 5, this would be a clock with 5 hours on it. And then boom, using this, you can now work in mod 5. So it currently shows 2 o'clock. Question is, what time is it going to be in 6 hours? Well, 5 takes you all the way back around, so it's 1 more than that. So 2 o'clock turns into 3. So 2 plus 6 is 8. So you could say it's going to be 8 o'clock, but on a mod 5 clock, you'd have to reduce that down to 3. So 8 and 3 are congruent mod 5. Okay, making sense? All right, that's your second metaphor. We're almost done for today, but I did promise you a final dropping some jargon about the ways in which you will see mods in the future. In the next video, we're going to discuss modular arithmetic. This section is called modular arithmetic. Not just mods, you don't just want to have them, but you also want to do arithmetic with them, adding and subtracting. So we'll talk about that next time. But first, let me get set up and I'll tell you a little bit about other ways in which this modular thinking, in which you take a bunch of numbers, like in working mod 5, let's work mod 10. Working mod 10, 2, 12, 22, 32, 42, 52, and you sort of consider those all equivalent or congruent or the same in some ways. That's a very important way of thinking that goes far beyond mods with the integers. So let me get that set up. So this idea of when you're working in mod 10, for example, of treating 22, 32, 42, 52, it's all being the same in some sense, being equivalent in this mod 10 sense. This is an idea that goes far beyond the integers. Now, within the integers, it is quite a home. I mean, pull up a number theory textbook and flip through it, and you're going to see a lot of mods. It is a very important tool in number theory. In fact, just very soon in maybe next video or two, we're going to look at Fermat's theorem. Fermat's theorem is an important theorem from number theory, which when you state the theorem, you need mods. When you prove the theorem, you need mods. It's just very core to that theorem. And that theorem naturally takes you off to cryptography, where in our digital world, mods are very, very useful in securing and having secure transfers of information. What else? Chinese remainder theorem, I was going to mention. Theorem from linear algebra, very important theorem. Is by far the best way to state it and understand it is using mods. Yet this, but again, this modding out idea of taking something and stripping away some unnecessary details, revealing the core of what's underneath, and doing so, by the way, in a way that changes the object that you're studying, and indeed focuses more on the relations between objects and the objects themselves. That idea is certainly not confined to numbers. I mean, you'll see it most prevalently in abstract algebra. If you take abstract algebra, you'll study groups, and then you'll study normal subgroups, and then you'll see what happens. You take a group and you mod out by the normal subgroup, okay? And then a month later, you study rings, and then ideals, and you ask, oh, what happens if we mod out by the ideals? You get these structures which resemble, in some ways, what you started with, but they're, in some ways, they're simpler, because they remove some of the excess. Well, that's one way to think about it. Other areas of math do this. Linear algebra has these factor spaces that are similar. Topology has quotient spaces. Even in analysis, you see this sometimes. I think LP spaces are defined in this quotient sort of way. So yeah, it's important, and it's gonna the broader idea is going to present itself time and time again in your education. I mentioned before, one key idea is to shift between objects and relations. That's another key idea that will be presenting itself time and time again in your math education. And I was going to mention one other thing. What was it? Nope, that was it. So, so that's it. Yeah, so I hope this is motivating to you, motivating to actually spend. It's going to take some time to really understand mods, but the time is going to be well worth it. And you're really going to, by studying mods, get your hands dirty with another sort of deeper idea, which we're going to play. If you really take the time now to understand it, it's going to pay dividends throughout the rest of your math education. All right, well, I think that's it. So I will see you. Oh, one more thing. My wife is always telling me that I forget to say something. So let's see what she has here. Okay, let's see here. She says to please like and subscribe and leave a nice comment. It really does help the channel. All right, you heard the woman. Go do that, and I'll thank you. Okay, see you next time. We'll continue our discussion of mods with some modular arithmetic. We'll start proving some stuff. All right, see you then.